Is Earth being watched by something not of this world?
Oh my gosh, what is that? What is that?
On July 1st, 2025, a pale, silent dot appeared just past Jupiter. It was nothing unusual at first, a slow blur tucked into the stars over Chile's Atacama desert. But as more data streamed in, scientists discovered something strange. The object wasn't circling the sun. It was on a straight path inward and fast. Within hours, astronomers would confirm what only 2 other times in history had ever been proven. A new object had entered the solar system, the third of its kind in recorded history. And whatever it wasn't slowing down.
Do we have the technology and the ability to intercept and deal with, in the future, anything alien?
Officially, no.
The global scramble. The first real signal didn't come from NASA. It came from a place far less official, a hobbyist observatory tucked into the volcanic plains of New Zealand. A lone astronomer named Sam Dean, watching the southern sky through a modest reflector, noticed a flicker. At first it looked like noise, a transient spike in the wrong quadrant, but when he ran it again, he discovered the object. Still there, moving, fast. He reported the anomaly to the ATLAS network, a sky-scanning system built for catching potential impactors, asteroids that might hit Earth. But this wasn't an asteroid. It wasn't bound to the sun. It wasn't even turning. The readings were clean. Its path was straight. Its name was assigned within hours. 3I/ATLAS, Third Interstellar, cataloged, confirmed. By the time NASA's Jet Propulsion Laboratory had clocked the object in their own data sweep, the numbers were already clear. This visitor wasn't from here. Its trajectory came from well beyond the Kuiper Belt. No origin star had been found yet, but it entered fast and steep, faster than Oumuamua, brighter than Borisov, a high albedo body moving against the drift of the ecliptic plane. It didn't match anything expected. Its spectrum showed traces of silicate ice, but mixed with something darker, metallic, even magnetic. Suddenly, what began as a single dot became a full-scale scientific scramble. Observatories in Chile, Hawaii, and South Africa were retasked. The European Southern Observatory redirected one of its high-resolution infrared arrays. Even the James Webb Space Telescope was given a brief window to log the anomaly. And across all instruments, one thing became clear. 3I/ATLAS wasn't breaking apart like other interstellar bodies. It was staying intact. Worse, its angle of approach wasn't random. It was direct, almost cleanly aligned with Earth's orbital path. The last time something from outside the solar system came in this fast, it left just as quickly, without warning, without answers. This one was different. This one was headed right for us. And as it got closer, more than speed, more than trajectory, what started to unsettle researchers most was the shape. Because no one could agree on what it was, not even the telescopes, not even the data. The shape that wouldn't stay still. At first, it was simple, a long blur spinning faintly in the sun's reflection. Most assumed it was oblong, like Oumuamua, a thin shard of rock, maybe cigar-shaped, maybe flat. But then the frames started to blur, not from motion blur, but from disagreement. Each instrument captured something different. From Chile's VLT, it looked narrow, angular even, like a blade. From Hawaii's Pan-STARRS, it showed a curve, a wide arc with no central mass. And when the James Webb images were processed, it appeared segmented, not broken or fragmented, a shape that flickered between forms depending on angle and exposure. A structure that shouldn't exist in a naturally formed body. It moved like a tumbling asteroid but held together like engineered metal. And worse, when infrared scans were overlaid, the temperature signatures didn't align. The edges were warmer than the center, not uniformly heated by the sun, actively radiating heat. The object wasn't just passing through space, it was responding to it. Researchers began to ask the obvious question. Was it spinning erratically or changing form? Was this a single object or a cluster moving in perfect sync? Even LiDAR-style data from Webb came back contradictory. And still, every hour, it drew closer, brighter, faster, more structured. NASA's software flagged unusual behavior in the light curves. The object dimmed and brightened at intervals that matched no known rotation pattern. But when someone ran those intervals through a harmonic calculator, something weird came up. The brightness pulses weren't random. They followed a rhythm, a series of repeating primes, a brightness pattern that pulsed every 11 seconds. Then 13, then 17. By the time this pattern emerged, 2 weeks had passed since discovery, and the object had crossed Mars' orbit. It was now deep within the inner solar system. still silent and unknown, but no longer unnoticed. And as it entered Earth's range of real-time telemetry, one final anomaly pushed the entire mission into red alert. When its reflectivity was measured one last time, scientists saw something strange. A flat signature, not diffused like rock or grainy like ice, but mirror-like. Whatever this was, it wasn't just reflecting sunlight, it was reflecting us. Unexpected signals. At first, it was just light. No sound or transmission of any kind. Just the strange reflective shimmer of something that didn't scatter light like rock or ice. But as the object moved into better range, roughly 100 million kilometers from Earth, radio telescopes across the southern hemisphere began to notice something strange. A very specific silence. The Australian Square Kilometre Array Pathfinder in Western Australia picked it up first. Then Arecibo's archived sensors picked up the same signature on a delayed trail from weeks earlier. What they saw wasn't a broadcast. It was a hole, a narrow-band radio shadow. One thin stretch of the electromagnetic spectrum had gone quiet around the object. Not distorted, not blocked by dust, just missing, as if the object was absorbing a precise slice of frequency. At first, the explanation was mundane. Maybe the metallic structure was absorbing the signal. Maybe the shape was creating interference. But the frequency in question, 4.83 gigahertz, wasn't random. It was the same frequency used by deep space communication arrays, a band reserved for long-distance telemetry, the kind used by probes, the kind used by Earth. But then another anomaly happened that changed everything. While scanning for residual noise in the quiet band, a PhD student at the South African Meerkat Array ran a reverse FFT, turning the radio silence into a waveform to map what was missing. But instead of blank static, the output returned a structure. The data team rechecked everything. Atmospheric interference was ruled out. Equipment errors discarded. Yet the result stood. The object wasn't just absorbing that frequency, it was modulating it, shaping the silence like a code. And then it happened. On July 21, 2025, a narrow pulse arrived at the Allen Telescope Array in California, lasting less than 2 seconds, riding the exact same 483 gigahertz band. It wasn't loud, it wasn't clear, but it was structured. 3 pulses, then 2, then 5. And for the first time since 3, I/Atlas had entered the solar system, it did more than reflect light. It spoke, or tried to. Because as the object moved within Venus's orbit, something even stranger began to happen, not in space, but on Earth. Suddenly, our machines started speaking back. Earth reacts. The message wasn't loud, it wasn't long, but it reached us. And in the quiet halls of observatories and research labs across the planet, something shifted. For the first time in years, SETI command logs were no longer theoretical. The event had moved from the fringe of probability to a hard-coded line in recorded history. A signal, short, narrow, mathematical, had arrived from an object not born of this solar system. And the world responded the only way it knew how, cautiously and with everything it had. At NASA's Deep Space Network headquarters in California, engineers rerouted every available dish. The Canberra station switched from Mars telemetry to full-spectrum signal lock. In Spain, technicians at the Madrid complex were instructed to isolate and mirror the object's broadcast band in rotating pulses. This wasn't about speaking, not yet. It was about showing we'd heard. But NASA wasn't alone. Within hours, the Chinese Deep Space Center in Jimusi pivoted its 66-meter dish toward the object's coordinates. The European Space Agency followed suit, coordinating a multi-country relay chain designed to maintain constant line-of-sight coverage as the object drew closer. Even the Indian Space Research Organization launched internal briefings on interstellar protocol. Notably, none of these actions were publicly announced. There were no press releases, no televised briefings, just a quiet ripple of activity behind the scenes. Radio schedules shuffled, software patched, internal alerts marked confidential. But one event forced the world's hand. On July 24th, 3 days after the initial pulse, a civilian radio enthusiast in Nevada posted a forum thread. He'd been scanning the 4.83 gigahertz band for fun. What he picked up was a brief, low-power tone, then a drop, then the same pattern, 3, 2, 5. And this time, it repeated, not just once, 5 times in a row, the same gaps, the same rhythm. The thread went viral, fast. Within 12 hours, the story broke into the public. Radio telescopes, military satellites, foreign ministries. For a brief moment, conspiracy gave way to confirmation. The object wasn't just present, it was aware. And it had chosen a frequency we use, one no natural body would isolate, one specifically human-made. This begged a question governments couldn't ignore. Was this a greeting or a test? And before anyone could answer, the object began to change, not in light or in signal, but in shape. The shape that shouldn't be. For weeks, the object had remained a featureless blur. No rotation, no flicker, no distinguishing features. It was unbelievably fast, but still nothing more than a dim speck against the sky. Until it wasn't. On July 27th, the first shift was spotted by a thermal imaging array at the University of Kyoto. Originally calibrated to observe Venusian atmospheric activity, the telescope caught an anomaly as it swept past 3I/Atlas's predicted path, a flare, a sudden spike that lasted less than 7 seconds, localized around the object's outer edges. It was faint, barely above background, but it was enough to raise flags. And when the Japanese team forwarded their findings to JPL for cross-reference, the pattern became harder to ignore. 3 days later, NASA confirmed it. The object's shape had changed. What had previously been a smooth, ovoid silhouette, a classic for fast-traveling asteroids, now showed subtle asymmetries. One edge pulled tighter, the other flatter. Even stranger, the thermal profile was no longer static. Pulses of internal heat were radiating outward like a slow heartbeat. The European Southern Observatory's VLT, located in Chile's Atacama Desert, also captured a high-exposure infrared composite of 3I/Atlas as it approached the inner solar system. The picture, when cleaned and enhanced, revealed something that defied categorization. A surface structure, long, narrow, and angled. Some dismissed it as artificing, a trick of light and resolution. But multiple independent arrays picked up the same pattern. This was not typical of any asteroid, comet, or known interstellar body. Natural objects do not reorient mid-flight. They do not maintain vector alignment. They do not develop structure in transit. But 3I/Atlas had done all three. Whatever this was, it wasn't a frozen rock riding cosmic currents. It was adjusting. And for a brief, silent moment, the possibility that had lived in the corners of theoretical physics started creeping into mission control logs. Because if it wasn't debris, and it wasn't a probe, then the final option, however impossible, had to be considered. Was it occupied? And if so, were we being observed? The observation window. For those monitoring the skies, the question shifted rapidly from "what is it?" to "how long do we have?" The mystery surrounding 3I/Atlas wasn't just about its shape or speed anymore. It was about access, because despite its growing notoriety, the object wasn't going to linger. By early August, 3I/Atlas is expected to pass within 4 astronomical units of Earth, about 600 million kilometers. Close by cosmic standards, but its trajectory is no gift to astronomers. It is slicing inward at a sharp angle, entering the inner solar system along a path that would take it behind the Sun. Calculations from NASA's Jet Propulsion Laboratory placed its perihelion, the moment of closest approach to the Sun, around October 30th. At that point, it would skim just inside the orbit of Mars, roughly 206 million kilometers from the Sun. But Earth would be on the opposite side. From our point of view, 3I/Atlas would vanish behind the Sun's blinding light.
It will arrive closest to the Sun when the Earth is on the opposite side, so we won't be able to look at it.
Because the period leading up to perihelion is the most scientifically valuable window. This is when researchers can observe sublimation, identify trace gases, and decode the object's internal makeup. It's when secrets get spilled. And in this case, most of that would be invisible to us. In response, international observatories have scrambled to coordinate resources. Japan increased the calibration of its lunar-based infrared system. France's CNES began a rapid response balloon launch in the stratosphere to avoid atmospheric distortion. Meanwhile, the European Southern Observatory fast-tracked time slots on its most sensitive instruments, hoping to capture a few uninterrupted nights before the object slipped behind solar interference. But the most ambitious move came from NASA's Deep Space Network, which reoriented its largest dish arrays to run a non-stop radar sweep despite uncertain return. Some questioned the logic, others understood the stakes. Because once 3I/Atlas dipped out of view, there was no guarantee we'd get another chance. The next window wouldn't open until early December, when it would re-emerge on the other side, cooler, dimmer, and farther away. If there was something to learn, something vital, it had to be done now. And perhaps the most critical data of all hadn't even been collected yet. Because deep within that venting gas, in molecules drifting silently into the dark, was the chemistry of another solar system. Chemistry of another sun. In the narrowing weeks before 31/Atlas slipped behind the sun, researchers focused their attention on the one thing that might speak louder than signals or shape: its composition. Because buried in the coma, the cloud of vapor and dust slowly bleeding off its surface was a molecular history book, the chemical fingerprint of a place we'd never seen. Spectroscopy teams worked around the clock. Instruments across the globe turned toward the object's tail, filtering its faint light into color bands, each one a clue: sodium, carbon, cyanogen. Every dip and rise in the spectrum told a story, and that story was beginning to sound familiar. Initial analysis showed something remarkable. The gases streaming from 3I/Atlas bore a resemblance to what we see in typical solar system comets: water ice, carbon monoxide, a scattering of organics. Not identical, but eerily close. It was unexpected. Most had assumed an object born around another star would be chemically exotic, unlike anything formed in our part of the galaxy. Instead, it looked strangely normal, or at least similar. That raised two unsettling possibilities. 1. Planetary systems across the galaxy may be chemically consistent. That stars separated by billions of years and trillions of kilometers might still bake the same molecules into their dust. That would mean life, at least the ingredients for it, might not be rare. Or 2, we're only seeing what 3I/Atlas wants us to see, because even as the comet-like signature became clearer, there were quiet inconsistencies. The gas ratios were just slightly off. The carbon-to-oxygen balance sat just outside known comet boundaries. One telescope even flagged a molecule no team could immediately identify. It wasn't alien, not conclusively, but it wasn't cataloged either. And that one anomaly became the focal point of every lab with the tools to chase it. Not because it was proof of anything, but because, if verified, it would make 3I/Atlas not just a visitor, but a message. The theory went like this: if a civilization wanted to encode information, they wouldn't use radio. They'd use chemistry, stable molecules or self-replicating compounds, carriers that don't decay across light years. But if that's what this was, then it wasn't just a discovery. It was contact. And contact always comes with consequences. Because the closer 3I/Atlas came to the sun, the more we began to ask a harder question. What happens when it leaves? The departure path. By the time 3I/Atlas began its return trajectory, pulling away from the sun and slipping past the orbit of Mars, one thing had become clear. Whatever this was, it came and went without hesitation. Its arc, first confirmed by orbital calculations weeks earlier, held perfectly. That meant it had never been captured by the sun's gravity. It had simply passed through. By early December, the object would have re-emerged from solar conjunction, finally visible again after weeks hidden behind our star. Telescopes across Earth scrambled to collect final data. The brightness had dimmed, the coma had thinned, and its distance was growing fast, measured now in millions of kilometers per day. By March 2026, 3I/Atlas would have cleared the outer planets. By 2027, it would be gone entirely, past Pluto, past the heliopause, and into interstellar darkness once again. No return, no trail to follow, just a vanishing dot slipping between the stars. And with it went our last chance to understand it up close. Its trajectory alone told us more than most comets ever could. At a relative velocity of nearly 70 kilometers per second, faster than any human-made spacecraft, it gave us proof that such objects aren't just theoretical. They exist, they travel, and they pass through our neighborhood with barely a whisper. But the bigger question that scientists and philosophers are all now quietly asking is this: was this a fluke, or are these visits part of something larger? Because 3 interstellar objects in less than a decade is a pattern. Before 2017, we had none. And now, we have a trail. Not of where they've come from, but of how many might still be on their way. And what's more important is what happens if the next one doesn't pass quietly. What if the next visitor slows down? What if it's not a rock at all? The pattern that shouldn't exist. If 3I's over, Atlas had arrived in isolation, it might have passed into history as a curiosity. A cold, fast-moving visitor that reminded us space is big, and sometimes strange things wander through it. But it didn't come alone, because now we have a pattern, a sequence, a quiet rhythm in the deep. In 2017, there was Oumuamua, the first object ever confirmed to have entered our solar system from interstellar space. It came from above the plane of the planets, tumbled erratically, accelerated without explanation, and left without a trace. No tail, no coma, no clear answers. In 2019, it was Borisov, a comet that looked far more familiar. It carried a visible coma, vented gas, and followed the kind of behavior astronomers expected from solar system bodies. But its speed and trajectory made it clear it too was from elsewhere. And now, 3I/Atlas. Bigger than Oumuamua, brighter than Borisov, and stranger than both. 3 interstellar objects, 8 years apart, each one with its own signature, its own behavior. But together, they form a line, statistically improbable and scientifically stunning. Had these objects always been passing through, and we were simply blind to them? Or had something changed? A shift in observation technology? Yes. But perhaps more than that. Some proposed we were entering a more crowded region of space. Gravitational currents from a passing star or the long-forgotten pull of the galaxy's spiral arms were sweeping debris from distant systems into our path. Others whispered something different, that maybe, just maybe, the timing was deliberate. Because what are the odds that 3 unique objects, each chemically distinct, each carrying unanswered questions, would all pass through during the brief moment in history when we have the tools to see them? We've had telescopes for centuries, but we've only had this level of precision for a heartbeat. And in that heartbeat, 3 messengers appeared, too close together, too unusual, too perfect. The skeptics are right to push back. Coincidence is not conspiracy, and space, by nature, is filled with outliers. But patterns are not born from hope, they're born from repetition. And if another interstellar object is spotted soon, one that mirrors the oddities of Atlas or carries echoes of Oumuamua, the argument will collapse into something harder to ignore. And once we admit that, we must finally ask, who or what is watching us from the dark? The eyes we've just opened. If the past decade has taught us anything, it's this: our solar system is not a sealed box. The illusion of isolation was never real. We just didn't have the means to notice the cracks in the glass. But that's changing now. We are, for the first time in human history, building eyes sharp enough to see the whispers in the dark, eyes that don't blink, eyes that can map the entire night sky in days and track the tiniest anomalies before they vanish into silence. And the most powerful of those eyes is nearly ready. Perched high in the Chilean Andes, the Vera C. Rubin Observatory is not just another telescope. It's a surveillance machine for the cosmos. With its 8.4-meter mirror and an unprecedented 3.2 gigapixel camera, Rubin will scan the entire visible sky every few nights, over and over again. That level of repetition isn't just impressive, it's revolutionary. Because it turns one-in-a-century detections into monthly alerts. It means no more missed flybys, no more decades of silence between signals. It gives us a chance to spot interstellar visitors not as they pass, but before they arrive. In fact, even during its early test phases, Rubin stunned astronomers by detecting over 2,100 new asteroids within hours. That was just the rehearsal. Once it's fully operational, Rubin is expected to increase our catalog of moving objects by orders of magnitude. More comets, more fragments, more anomalies, and very likely, more objects like 3I/Atlas. For scientists, this presents a thrilling problem. What do we do with a sudden flood of data from objects that weren't even supposed to exist in our field of vision? How do we classify them, study them, reach them? For engineers and mission planners, it creates new urgency. Missions once thought impossible, like intercepting an interstellar object, suddenly feel within reach. If we have warning, we can prepare. But for everyone else, philosophers, dreamers, and quiet observers of the stars, it marks a more unsettling shift. If we keep watching, we will see more. That's no longer a question. The question is what we'll do when something finally sees us back. If this was just a comet, it forces us to reconsider how the planetary systems across the galaxy might be more alike than we imagined, which means the origin of life is possible, anywhere. And if this was not just a comet, if even the smallest details hint at something crafted, something unnatural, then we are standing at the edge of a conversation we didn't know had already begun. What comes next may not be silent, it may not be fast, and it may not be content to leave without leaving something behind. Do we keep searching, or do we wait for the next one to find us?